Good evening, everyone. So today is the week 4 for this course Digital Signal Processing and Application. So today we'll have a tutorial session for the topics covered in the week 4 for this course on NPTEL portal. And this video will be recorded and will be uploaded on YouTube. So those who cannot watch at this time can watch it later and comment in the YouTube section also for if they have any doubt. So we'll wait for just 1 more minute and then we'll start our lecture today. So let us start the today lecture. So our first question is, suppose the DTFT of just a minute. Suppose the DTFT of a discrete time signal xn is x omega. So the DTFT, the discrete time Fourier transform is x of omega. So which of the following is true? So as we know the property of DTFT of any discrete time signal. So DTFT of any discrete time signal is periodic with 2 pi. Is periodic with 2 pi. So x of omega plus pi is equal to x of omega minus pi. So this option will be correct because here you can see uh, x of omega plus pi is equal to x of, or we can write like this, x of omega minus pi is equal to x of omega plus omega minus pi plus 2 pi because it is periodic with 2 pi. So we will get hello. So we will get x of omega minus pi is equal to x of omega plus pi. So option number C is the correct answer. Okay. So this is just the basic property of discrete time Fourier transform of any signal, that it is periodic with period of 2 pi. So now we'll see the next question. If you learn it out, you can ask. The second question is, if the Fourier transform of the discrete time signal xn is equal to 2 by 3 to the power n u of n plus 3. So the Fourier transform x omega is given as 8 e to the power of 3 j omega divided by 1 minus 2 by 3 e to the power of minus j omega. Okay, so, this is given. So now what we will do, we will take y of n, or we know that, like, first I will write in the general form, like a to the power of n, u of n. So what is the PTFT of this? As we have derived in the last tutorial session also, this will be 1 by 1 minus a to the a into e to the power of minus j omega. Okay, and so the same thing we will do here. So let's take a is equal to 2 by 3 to the power of n u of n. So the DTFT of this signal will be 1 by 1 minus 2 by 3 e to the power of minus j omega. Okay. So now what we will do, we will take 2 by 3, we will substitute n tends to n plus 3. Okay. So now to substitute this value, so we will get 2 by 3, n is tending to n plus 3. So it will become n plus 3 u of n plus 3. So the DTFT of this will be, let's suppose this is our y of n, and this is our y of omega. So the DTFT will become e to the power of 3j omega into y of omega. So this is also one of the property. So after this, we will get equal to e to the power of 3j omega into 1 by 1 minus 2 by 3 into e to the power of minus j omega. Okay. So 2 by 3 whole raised to the power n plus 3 u of n plus 3. So the DTFT of this is given as this. So now what we will do, this we can write as 2 by 3 into n multiplied with 2 by 3 into 3. So this time is 8 by 27. So now multiply with 27 by 8 on both sides. Okay. So after this, we will get uh, this side we will get 2 by 3 to the power n u of n plus 3 because this 8 by 27 when multiplied with 27 by 8 on left hand side will become 1. So the DTFT will become 27 by 8 into e to the power of 3j omega divided by 1 minus 2 by 3 e to the power of minus j omega. So the correct answer for this, like there is no option. So this is just a selective question. So this is the answer for this question. Now we'll move on to the next question. If you have any doubt, you can ask here. So the next question is find the convolution of the signal x1n and x2n where un is the unit step function. So we have to find the convolution. So find the convolution of this signal. So now, so we know that convolution in time domain is equal to multiplication in frequency domain. Okay. So what is our x1 n now? So we have to just find the Fourier transform of x1 n, that is x1 omega, and for x2 n, that is x2 omega, and we have to multiply it to get the answer. So it's a very simple question. So our x1 n is given as 2 to the power of minus n u of n, and our x2 n is equal to 3 to the power of minus n u of n. Here un is the unit step function. Hmm. So we will first find the like Fourier transform of this x1n and x2n. So for Fourier transform of x1n, what will be our x1 omega? This is simple a to the power of n un, like what we have done here. So this is very important. So this will be 1 by 1 minus a to the power of e minus j omega. So this will be our x1 omega will be 1 by 1 minus a. A is here. See, if it is 2 to the power of minus n, this can be written as 2 to the power of minus 1 to the power of n. So a is our 2 to the power of minus 1. So this will become e to the power of minus j omega. Now again, x2 omega, this is again 3 to the power of minus n. So this will be 3 to the power of minus 1 to the power of n. So that is equal to 1 by 3 to the power of n. So x2 omega will be 1 by 1 minus 1 by 3 e to the power of minus j omega. Okay. So this is our x1 omega and x2 omega. So convolution of x1n and x2n is given like the this is given as multiplication of x1 omega into x2 omega. So we can write it as 1 by 1 minus half e to the power of minus j omega into 1 by 1 minus 1 by 3 e to the power of minus j omega. Okay. So for matching with the option, like option is in the decomposed form. Our answer is in multiplied form, so we will decompose it. So we can write as, when you decompose, we can easily decompose like this by 3 by 1 minus half e to the power of minus j omega minus 2 by 1 minus 1 by 3 e to the power of minus j omega. So you can find this, you will get the same answer because this 3 minus e to the minus j omega will cancel it out. So we'll get the, this is equivalent to this only, decomposed form. You can also do decomposition by doing a by 1 minus 1 by 2 e to the power of minus j omega plus b by 1 minus 1 by 3 e to the power of minus j omega. So this will become a minus a by 3 e to the power of minus j omega plus b minus b by 2 e to the power of minus j omega. This is our numerator. And this we have to equate with is 1. So a plus b is equal to 1 and also minus a by 3 plus b by 2 is equal to 0. So in this way we will get a by 3 is equal to minus b by 2. Then we will get 2a is equal to minus 3b. So when you substitute 2a is equal to minus 3b, you will get minus 3b plus 2b is equal to 1. So b is equal to minus 1 and a is equal to b is equal to 2a is equal to minus 3b. So when you substitute 2a plus 2b is equal to this side it will be 2 because we are just multiplying with 2. So 2a plus 2b is equal to 2 and substitute this here. So minus 3b. So b will be here minus 2. So a will be 6 by 2 that is equal to 3. So same value is there. So now we can write it as 3 3 into, and this is our 1 by 1 minus 2 x1 of omega minus 2 into this is our x2 of omega. Okay. And using linearity, what we can do, like the linearity property. So the inverse GTX will be 3 x1 of n minus 2 of x2 of n. Okay. So which is the correct option? 3 into x1 of n. So 3 into 1 by 2 to the power of n un plus 2 into, sorry, minus 2 into, yeah. So this option is the correct option. Option B is the correct answer for this question. So if you have any doubt, you can ask. So we'll move on to the next question now. Suppose the discrete time signal xn is shown in the figure below. The number adjacent to any dot represents the value of the signal at that instant. So this is the value of the signal at that instant. Okay. It is given that xn is equal to 0 for all n such that n is greater than equal to 2 or less than equal to minus 4. So for these value xn is 0. It takes omega to know the dtft of xn. So what is the value of x omega d omega? So this is a very good question. So in this question it is given the dtft of xn is x of omega. So we know that the inverse discrete time Fourier transform equation xn is equal to 1 by 2 pi integration over minus pi to pi x omega e to the power of j L omega d omega. Okay, so now let's substitute here uh, n is equal to 0. We will get x of 0 is equal to 1 by 2 pi x omega into e to the power of 0 d omega. So now multiply, we check this 2 pi this side, so we will get 2 pi x of 0 is equal to integration of minus pi to pi x of omega d omega. So we have to find this. So answer will be 2 pi into x of 0. And we know that x of 0 is given in this question is equal to 5. Okay. So the final value will be uh, 2 pi x of 0. So that is equal to 10 pi. So correct answer is option number B for this question. We'll solve this question at the end because this is a little lengthier question. Before that, we'll try to finish all other questions. Suppose the signal xn is given as impulse function del of n minus 2 plus del of n plus 2. So, what is the, like, how to define this function? At n is equal to 2, let's suppose this is the axis of n, and at n is equal to minus 2, there will be a impulse. Del n is the unit impulse function. So, what is the Fourier transform of the signal? We know that for any signal x omega, the like for the Fourier transform of xn, x omega is given as xn e to the power minus j omega n summation over n is equal to minus infinite to plus infinite. Okay. So now when you substitute all this value, look the value is that n is equal to 2 and n is equal to minus 2. Okay. So this will become x of 2 e to the power of minus j 2 omega plus x of minus 2 e to the power of j 2 omega. Okay, understood up this step? We have just see for all n the value is 0. See, for 0, for 1, for minus 1, for 3, for all these value the value is 0, and for n is equal to 2 and minus 2 value is 1. So this will become 1 into e to the power of minus 2j omega plus 1 into e to the power of 2j omega. E to the power minus 2j omega plus e to the power 2j omega. What will be the answer? So this answer will be cos of 2 omega minus j sine of 2 omega plus cos of 2 omega plus j sine of 2 omega. Answer will be 2 cos of 2 omega. Okay. So the correct answer is option A. Okay, this is also a very lengthy question, but we'll solve it now. So we have to solve this integration using the Parseval's theorem. So we can also solve this integration using normal theorem, like just by the trigonometric transformation we can apply and we can solve. But we have to solve using the Parseval's theorem. So value of I is given as minus pi to pi. So here it is 65 is there. So what we will do, we will write 64 minus 16 cos omega plus 1. Okay. Now for this 1, we can write it as cos square omega plus sin square omega. We will also apply Parseval's theorem, but before that, we will do some simplification to make this integral simple. So I is equal to, for 64, we can write it as 8 square minus 2 into 8 into cos omega plus cos square omega. Okay. And there will be additional sin square omega d omega. So what I will become 8 by 8 plus cos omega, sorry, 8 minus cos omega plus j of sin omega mod of square. Because see, if you do the denominator term, what we will get? We will get the same value, like this is the magnitude value. So when you do, you will get a square root of 64 plus cos square omega minus 2 into 8 into cos omega plus the magnitude of sin square omega. Okay, so this we can write now. Let x of omega is equal to 8 by 8 minus e to the power of minus j omega. Like this is the Fourier transform. Let's suppose this is the Fourier transform of any signal xn. Like xn, the Fourier transform of xn is x omega, and let's assume x omega is this value. So we can show that like xn is equal to 8 to the power of minus n e to the power of minus j omega, because see, the Fourier transform of this will be how much? The Fourier transform of this will be 1 by 1 minus 1 by 8 e to the power of minus j omega. So this will be nothing as 8 into 8 minus e to the power of minus j omega. Okay. So this value is our x of n. So now according to Parseval's theorem, summation of mod of xn square is equal to 1 by 2 pi x of omega mod square d omega. So this is a equation for Parseval's theorem. So now we will use this. So we will get minus pi to pi x of omega mod square d omega is equal to 2 pi summation of xn square. Okay. Now summation of mod of xn square is equal to summation of so our xn is xn square is 1 by 64 to the power of n. So this will be 64 by 63. So basically I will be 2 pi into 64 by 63. So this will be, because the magnitude of xn will be here 64, like 1 by 64. Okay, because 8 to the power of minus n. So mod of x of n will be xn square will be 1 by 64. So this will be 128 pi by 63. So the correct answer is option number B. So now we'll move on to the next question. A filter has impulse response input xn is equal to 3 to the power of minus n u of n. And input signal xn is applied to the filter, that is given as 2 to the power of minus n u of n. So find the energy spectral density of the output. So we know that output energy spectral density is equal to magnitude of the system response square of that multiplied with input energy spectral density. So, so first we'll find now h of omega. So y of, so this is the equation. So now h of omega will be 1 by 1 minus 1 by 3 e to the power of minus j omega mod square, and x of omega will be 1 by 1 minus 1 by 2 e to the power of minus j omega mod of square. So the magnitude of this will be, so answer is in the term of cos omega and j omega. So we'll substitute 1 by 1 minus 3 cos omega minus j of sin omega. So this will become, so we can write it like this. Now what we can do, we will normalize this. So we can multiply with the 1 minus 1 by 3 cos omega. So we will multiply with the, like 1 minus 1 by 3 cos omega minus of 1 by 3 j of sin omega to the numerator and denominator here, and here uh, minus of j by 2 sin omega. So after doing all this, like we can do, just give me a second. So we can normalize this, and the final answer we will get as this option C. So like this we can write as this also, 3 by 3 minus cos omega plus j of sin omega, and here 2 by 2 minus cos omega plus j of sin omega. Now multiply with the 3 minus cos omega minus j of sin omega. So when you do this, so it will become 9 plus cos in the denominator, 9 plus cos square omega minus of j square plus of sin square omega. So denominator will be 10. So this will become 10. So similarly, our answer will be 3, 3 minus cos omega minus j sin omega divided by 10. It will become 2, 2 minus cos omega minus of j sin omega, and this value will be 5. So now we can easily calculate and you will get option number C. So now we'll move on to the next question. The set X is given, like the three vectors are given, is an orthonormal basis of three-dimensional and in three dimension. Find the coordinate vector of U relative to this basis. So like vector U is given as minus 3, 2, comma 5. So there is a formula like the relative to this basis U dash vector will become vector U into vector V1, comma vector U into vector V2, comma vector U into vector V3. So this will become 2 by 7, 6 by 7, 3 by 7 into minus 3, 3 by 7, 2 by 7 minus 6 by 7 into 2, 6 by 7 minus 3 by 7, 2 by 7 into 5. So we will get, so the final answer we will get as this. Now xn being a complex value discrete signal whose DTFT is denoted by x omega. So the DTFT of xn is x of omega. So let xn is equal to x r of n plus j of xc of n. So that is the real component of x and the complex component of x. Where xr and xc are both real valued signals. What is the DTFT of x of r of n? So we have to find the DTFT of this. So xr of omega is equal to half of DTFT of x of n plus DTFT of xn bar. So we know that x of omega is equal to xk e to the power of minus j omega k. So DTFT of xn bar be, let's suppose y of omega. So y of omega is equal to x of k bar e to the power of minus j omega k. And k is equal to minus infinite to infinite. So we can write it as x of k. And if you do whole bar, then here it will change e to the power of j omega k. So now this will become xk e to the power of, sorry, it is the same thing. So here this can be written as x of minus omega bar. So our xr omega, that is given as 1 by x of omega plus x of minus omega conjugate. So today we'll stop the lecture here only, and we'll meet on next Tuesday again. So if you have any doubt, you can ask. Sorry, here it is x of r omega. So this is half of DTFT of xn and DTFT of xn bar. So DTFT of xn bar is this. So answer will be this. So thank you everyone for attending today's lecture. We'll meet again on the Tuesday at the same time. Thank you.